I'm going to be looking at this screen, but talking into this webcam, so I'm not being ignorant. My stuff's this side of me. And a little confession, it's called the Asteroid Belt, but it might as well be called Ceres and Friends, because when you start looking into the Asteroid Belt, everybody talks about Ceres, and Ceres is probably the most interesting thing in there. Nonetheless, I hope it's still interesting, and I've still tried to cover as much of the Asteroid Belt as reasonably possible. So to get started, I thought I'd say why I wanted to talk about the Asteroid Belt, and mainly it comes from growing up at the back end of the 90s and a few pop cultural references in there that have been instilled with me since a young age. So I remember being about 3 or 4 years old, and you'll see that, yeah, brilliant, and playing Missile Command, sat on my dad's knee, probably about 3 or 4 years old, and the idea is that you shoot down asteroids, meteorites, whatever you want to call them. And then that progressed, and eventually I got to play on Asteroid, and you, for some reason, fly around space and shoot at small rocks and also depth charges for whatever reason. Back into the 90s, as far as I can remember, there were some pretty awful films out as well. Armageddon, where the story is an asteroid is plummeting towards Earth. Only Bruce Willis can save the day by landing on the asteroid, drilling to the center of it, detonating a nuclear weapon, and managing to escape unscathed. And finally, Star Wars as well, where Han Solo flies through an asteroid field. Not the most accurate representation of an asteroid field, where the rocks are probably about 100 meters across and flying back next to each other. The real thing is nothing like that at all. So, oh yeah, and the final thing is, a couple of years ago, I was working on an alloy as part of my undergraduate studies, an alloy which was 95% cerium, and cerium has a special connection to the asteroid belt through the minor planet Ceres. So, today we're going to talk about why should we care about asteroids, and talk about Ceres and the discovery of that as the first asteroid. And then we'll talk about some other notable features which are not Ceres. Some asteroid belt probe missions, so past, present, and future, with an emphasis on NASA Dawn, because that was the most recent one and by far the most fruitful. And talk about future interest in asteroids and why it's important to start developing an understanding of them now. So bit of a boring slide. I'm not going to dwell on it too long, but basically it's important to know an asteroid is a small rocky body that orbits the sun, but is generally considered too small to be a planet. A meteoroid can be thought of as an asteroid that's been fragmented through collisions. A meteor is anything that burns up in Earth's atmosphere, and a meteorite is anything that makes it to the ground. Comets are quite similar to asteroids in that they orbit the sun, but their composition is different. They're generally ice, gas, and dust rather than rock, although Ceres, again, is a bit of an exception in that it's rock and ice. So why should we care? Well, the most obvious reason to show is the Chicxulub impact crater in Mexico, and this is the impactor that wiped out the dinosaurs. So at the most fundamental level, it's quite useful to know where these things are, and if any are going to be heading our way anytime soon. Not that we'll be able to do much about them, we don't think, but there we go. Prospects for prospecting in the future. These things are generally quite mineral rich. Some of them have been estimated at many hundreds of billions of dollars worth of resources. How feasible it is remains to be seen, but maybe in the next 100 years with the space industry taking off, literally, we might start to see this as a prominent industry. And third, and finally, is the search for extraterrestrial life. People talk about this with all heavenly bodies, but you know, there are things out there with volatiles on them, water trapped under the surface. Ceres, again, is one of them. There's a chance that it could be harboring life somewhere in some form. So Ceres, it was the first asteroid to be discovered, and it was named for the Roman goddess Ceres of the harvest, agriculture, and motherly relationships. And a year later, element 57 was isolated in Sweden and took its name from the asteroid and became Cerium. On the picture on the left, we can see Ceres, Bacchus, and Venus from ancient Roman mythology. In the picture in the center, we can see Demeter, Persephone, and Hades. This is the Greek equivalent myth. Demeter is the mother of Persephone, who of course goes down to the underworld with Hades, eats the 6 pomegranate seeds, gives us six months of darkness, 6 months of light, and gives rise to the seasons. And on the right is this chap, John Jacob Berzelius. He was from Sweden, and he was the guy who isolated Cerium the year after Ceres was discovered. Quick history lesson. So in about 1600, the notable astronomer Kepler conjectured that there's an apparent gap between Mars and Jupiter, and noted that their orbits are slightly misaligned. and with good reason. In 1772, Bode, another brilliant astronomer, predicted the gap could be occupied by an undiscovered planet. This was motivated by his theory with Titus, the Titus-Bode law, which essentially says that planets further out from the sun get twice as far apart from the previous one. So that would mean that Jupiter is twice as far out from Mars, Saturn twice as far as Jupiter, and so on and so forth. For the outer planets, this was generally quite true. I think Neptune threw up a few issues with the rule, and it's now been disproved. But certainly in 1788, Herschel turned his telescope to Uranus, and there was a planet waiting for them exactly where this model told them they would be after the orbit of Saturn. Gave them quite a lot of confidence in the rule. And in 1800, the Hungarian astronomer von Zach commissioned a task force of 24 of some of the best astronomers in Europe at the time to try and locate the Mars-Jupiter gap planet. This team ran successfully in finding Ceres, but did go on to locate other large asteroids, so it wasn't a complete failure. Ceres instead was observed on New Year's Day in 1801 by an Italian chap called Giuseppe Piazzi at Palermo Astronomical Observatory in Italy. Palermo is the capital city of Sicily, so quite a nice place to be doing science, I suspect, even 200 years ago. He was initially out looking for the 87th object in Lassale's catalogue of zodiacal stars. Now, I did have a quick look at what this was, didn't find very much, but the 87th object didn't exist anyway, as we'll soon find out. So this was Giuseppe at the top, map of Italy showing you roughly where Sicily and Palermo is, and the observatory is still standing fine today. And this is Ceres, not how Giuseppe Piazzi observed it, but how we see it today. Instead of a star, Piazzi found a moving object. He first reported it as a comet, as was standard practice, but then claimed it could be something far greater, noting that it was moving too slowly to be a comet. So he didn't rule out the fact that it could have been a planet. And it went on for the next few decades being referred to as a planet, although it was quite challenging to find. In the 1850s, however, or by the time the 1850s came around, several other objects have been located near the orbit of Ceres, and they were all classified, or in the case of Ceres, reclassified as asteroids. And nowadays it's classified as a minor planet. It's the only one inside Neptune's orbit, and it's also the 25th largest body between Sun and Neptune, which is quite remarkable when you think about the number of moons of Jupiter and Saturn, especially. Pre-2006, it was considered an asteroid, albeit a very, very big one. In 2006, I'm sure we all remember that Pluto was reclassified as a dwarf planet, and any prior attempts to make Ceres the 5th official planet from the Sun were basically quelled. And after 2006, as it says at the top, it's now a minor planet based on criterion 3, which was introduced in 2006, and I'll talk about that. Pluto does meet the requirement, Ceres doesn't. Pluto is a dwarf planet and Ceres is a minor planet. So the IAU, which is the International Astronomical Union, defined pre-2006 a planet as being two things. They must have a sufficient mass to achieve plasticity, and that is to say they're very heavy and they can crush themselves and morph into a spherical geometry under its own gravity, under their own gravity. Ceres does this. It is quite, apologies, it is quite round. And also, the object must orbit a star and must not itself be a star or a satellite of a planet. So it can't be a moon, it can't be a star. It needs to be something ideally rocky. And again, Ceres meets this criterion. In 2006, however, the additional rule that it must have cleared its neighborhood of debris was introduced. Pluto, of course, clears this by a mile. There's nothing really near it other than the Kuiper Belt, and even that's pretty far out. The Oort cloud is orders of magnitude away. Ceres, it'd be quite a task for Ceres to try and clear its orbit, considering it's smack bang in the middle of the asteroid belt. So it fails at this hurdle. And you can see there's a little cartoon strip I've done there. Ceres says, "Make me a planet," and the IAU say, "Surely you can't be serious." And he turns around and says, "I am Ceres and don't call me Surely." Moving swiftly on. Ceres is the largest object in the asteroid belt, and it accounts for about 30% of the total mass in there. And I want to convince you tonight, if you haven't been convinced already, that it's far more than just a rock in space. It's massive and it has some very interesting properties. On the back of that, on the flip side, it's also the smallest object we know of to achieve sphericity, which again is quite a unique feature and plays off its large size as an asteroid. Here's Ceres to scale. So our moon is the white circle you see encircling Pluto and Ceres. Ceres is about 1/3 to 1/5 the radius of Pluto, so it's not insubstantial. Not by any means. And here it is against Vesta, another large asteroid, Charon, the moon of Pluto, and Pluto itself. Just to give you some quick fire numbers, the mass is about 940 billion kilograms. And again, as I say, it makes up about a third of the asteroid belt's weight mass. This is up from a previous estimate of 25%, and the correction came from measurements made on Dawn in 2015. Has a radius of 277 miles, so approximately London to Scotland, depending whereabouts you are. It orbits the sun every 4.6 Earth years at a distance of 2.8 astronomical units, and it reaches opposition every 15 to 16 months. Now, as it fluctuates, its apparent magnitude changes from 9.3 up to 6.7. So it's difficult but not impossible to see, as Piazzi found out. But I've never tried it and probably never will. And it'd be great to know if any of you guys have. It'd be really interesting. Cererian, I was told, is the correct adjective, not Ceresian, but a Cererian day lasts a little over 9 Earth hours, so 9 hours and 4 minutes, I believe. And it's geologically interesting. It's thought to be 60% rock and at least 30 to 40% ice. We're not sure, not 100% sure of its structure, but we think it's going to be some sort of hydrated, muddy, bentonite, clay-like material. And some have even proposed a metallic core, but this does seem unlikely. So to talk about its geology and mineralogy, we need to take a step back to 2004. And the best thing we had at taking images at the time was this guy, Hubble. The Hubble Space Telescope in 2004 produced this image of Ceres, which is, you can literally count the pixels that comprise it. And then in 2015, Dawn quite literally dawned on Ceres, and we found some more detail. So in this image, you can see a few specks. Hopefully you can see in the north and the western quarters, you can see these bright spots. And with Dawn, this is the Dawn probe. We start to elucidate on them a little bit clearer. So this is in January 2015 when it first approached Dawn, and here's May 2015 when it entered, when Dawn entered Ceres's orbit. And you can see these bright spots here are much clearer, and we see them as individual blots rather than quite large puddles as they appear from Hubble. If we look even closer, that's no moon, and that's a failed joke because neither is Ceres. And yeah, as Dawn moved closer and closer towards Ceres, we got higher resolution images and at higher magnifications. Initially, these bright spots appeared to be decorating the rims of craters. So the idea was that icy bodies were impacting in Ceres and depositing material around the rim. But as we got closer and closer, or as the probe got closer and closer, we see that the material is actually quite concentrated in the center of these rims, of these basins, and we think this points to volcanic activity. Dawn's onboard spectroscopy detected sodium lines, sodium being obviously a key indicator for salt. Complex salts, so not just sodium chloride and sodium iodides, but also ammonium salts as well, organics and volatiles, which you wouldn't necessarily expect to find in an asteroid, are present. And we think that these have come from saltwater deposits spewing out of the surface. The water then sublimes on the heat of the sun, or through space weathering effects, leaves behind the salty deposit, the briny deposit, and this is what we see in images. Now, the fact that we can still detect volatiles and organics from an object which we think is getting on for about 4.5 billion years old is quite impressive, and tells us that actually it's quite geologically active. Something underneath the surface must be ticking over to keep that surface material present. And also, although it looks quite cratered like the backside of the moon, it's actually a lot less battered than we would have expected it to be, considering it's smack bang in the middle of the asteroid belt. And again, we think that regolith is being deposited from these eruptions. Ceres is far too cold to be erupting magma, and we think the volcanoes are actually cryovolcanic spewing up icy water. So this is a major crater called the Haloni crater, and this is a complex example where you can see actually the prominences in the center, and in enhanced color imaging, we see the deposits around the edge and a concentration in the center again, which indicates some volcanic activity. There are two models proposed for the structure of Ceres as a result of this. In both of them, we tend to see a porous, quite fractured crust, and this is because of ice migrating its way out into space. Obviously, freezing, contracting, shrinking adds a lot of stress to the dry crust. The inside is where the two models differ. We think one of them might have a very wet mantle, perhaps a 50-50 ratio water to rock. and in this instance, no rocky core. This could continue all the way through, whereas the second model on the right here is about 50-50. It's got about a 50% by volume core of dry solid rock and 50-50 clay-like mantle containing all the water. And both models, interestingly, predicted to at least 50% by volume of H2O. So definitely worth exploring further. An interesting topological feature on Ceres is Ahuna Mons, or the Lone Mountain, as it's known in English. It's quite a unique feature on Ceres. It's a single protrusion. There's nothing else like it on the surface. It's about 20 kilometers in diameter and about 5 kilometers high at its peak. We're not really sure what could have caused it, other than one hell of a volcano to leave such a, if it is salt, to leave such a big salt deposit behind. I should say that all these images are from NASA, except for this one in the top right, which was reconstructed from the European Space Agency. Yeah, nothing else like it. The only real theory that we have, the only plausible theory as to how this came to be is through the impact antipole model. And this is essentially where, if you think on the reverse side of the planet, you have a very high impact force from basically an asteroid collision. And this would send a seismic shockwave around the planet. And when, by the time it meets and joins back up at the other side, you get a big fault line occur. This could fracture the surface, allow a huge eruption of cryovolcanic fluid, leading to this big salt deposit. Now, this hasn't been directly observed on Ceres and probably never will be, but we have seen similar things happen on Mercury, and that's really where the theory came from. It's the only plausible reason that it could have happened, we think. Just to show you a cryovolcano, very similar to a volcano on Earth with magma, but instead you've got icy cold water. There's the porous and stressed out crust through which the icy water can penetrate, leaves behind a salty deposit, and also it disrupts the local regolith as well and replenishes that surface. In terms of atmosphere and habitability, it's not really big enough to retain its own atmosphere. There's nothing really there long term, other than perhaps water vapor from impact collisions and also from cryovolcanic eruptions, but this would soon dissipate into space. There are, however, large volumes of water beneath the surface, as we've seen, which could harbour the ingredients for life, including volatiles and organics. And the water in certain craters on Ceres doesn't necessarily sublimate, and we think that even in some of the deepest craters there could be some liquid ice, some water ice left, because Ceres only has I believe it's a 4-degree axial tilt, which means that some of the craters never see sunlight and haven't done for billions of years. In which case the ice would, in theory, remain. So charting the first asteroids, I did mention on this slide that I'd come back and talk about some of the other objects as well. The most notable ones are Pallas, Vesta, and Hygiea. Pallas is the largest, and it's also the brightest asteroid, including more bright than Ceres itself. Vesta was the first to be discovered after Ceres in 1802 by this guy Heinrich Olbers. 5 years later, he also discovered Pallas. And it took about half a century later for this Italian guy Gasperi to discover Hygiea as well. And together, these three plus Ceres make up about 40% of the mass of the asteroid belt, which is quite phenomenal when there are literally millions of objects out there. So what is the asteroid belt itself? It can be described as a toroidally shaped disk or a donut shaped disk. It sits between Mars and Jupiter and spans a disk of about 2.2 to 3.2 astronomical units. We think there are up to 2 million objects with a diameter bigger than 1 kilometer in there, and many millions more that we haven't tracked or haven't detected of a much smaller size. The total mass is on the order of that big number there, which seems substantial, but actually it's only 4% of the lunar mass. So it's actually quite a low density region of space. There are three main classes of asteroid based on spectral lines. So we have C-class, S-class, and M-class. C-class being carbonaceous, S-class being siliceous, and M-class being metal-rich. Metal-rich might be the ones that we try to mine in the future. Non-belt asteroid populations also exist elsewhere. So we have near-Earth objects and asteroids. We have Kuiper belt objects, Oort cloud bodies, which are about 5,000 astronomical units away. but necessarily, but these do also exist. It's important to note. So it was proposed in 1802 by Heinrich Olbers, the guy who discovered Pallas and Vesta, that Pallas and Ceres were fragments of a shattered planet. Now, even at the time, this was sort of looked down upon, and especially now that we know how much mass is roughly there, we know this can't really have been true. There's such a low mass in this region of space that it seems unlikely it came from a single large planet. And also, you need an incredibly high impact force to be able to literally shatter a planet into millions of shards. And now with modern equipment, we've been able to determine that the compositional variation is so large between these different bodies that they couldn't have come from a single homogeneous or even layered planet itself. More recently, in 2018, researchers at the University of Florida suggested that they're actually fragments of many ancient planets from before the formation of our own solar system. So in normal solar system formation, you'd have the accretion of dust and gas to form stars that ignite and give you a thermonuclear fusion reaction. And for planets, generally it's rock and dust gas. However, at some point in time, Jupiter was formed, quite rapidly made its way through the inner solar system, and prevented some of this accretion from occurring. At this point, things like Ceres may have already started to form. It would have been at the protoplanet stage, so it was relatively large, had quite a significant gravity, but the pull of Jupiter stopped it from becoming a fully fledged planet. And you can see in the diagram that's been spinning there for about 5 minutes and giving me a headache. You can see that Jupiter really does kind of protect us from these objects. It really does hold them back for us. But Jupiter, it's not always a good thing. It does have quite a large gravitational effect on the asteroids in there. It accelerates them to very high speeds and they can impact on one another. And again, in the early solar system, it's thought that these impacts and these collisional events were more frequent than the accretion, than the likelihood of an accretion scenario. And thus the net effect is that you get a reduction in planetary size rather than an increase. I just want to show you this video now very quickly. Hopefully I will be able to show you this. It's only about a minute long. Yes. And hopefully you can see the screen. Is that correct? Has anything changed for anybody? Or
your video's now running.
Oh, brilliant! Fantastic. Right.
Okay.
So this is really just a catalogue. Hopefully it's running.
Click the play again.
Yeah, it's frozen on me.
Click the play.
Yeah, it's frozen, Paul. It's not allowing me to carry on. Ah, there we go. So this is basically a catalogue of the last 20 years of the asteroids that we've known about. So the things in blue are near Earth asteroids, and the orange are the main belt asteroids. So in 1999, we knew of a few of these objects and could track them reasonably well. 2009, we discovered quite a few more near Earth objects, began to get a little bit more scared. 2018, there's a hell of a lot more. And then when we bring in the additional asteroids from the asteroid belt itself, there are millions and millions and millions of objects. So it's quite important that we keep tracking them all as best as possible. So hopefully. You should be able to see my presentation again.
We're back to your presentation.
Fantastic. Right, so we'll talk about the past missions to the asteroid belt then. Does anybody have any guesses as to what this probe was? The clue is that it was launched in 1972.
Pioneer 10, I'm the only one talking.
Yeah, fantastic. No problem, Paul. A bit one-sided. Yeah, Pioneer 10, you're absolutely right. I thought I was going to teach somebody something there, but clearly not. It was launched in 1972, and its mission was to orbit and image Jupiter for the first time in any real sort of detail. and historically it became the first probe to traverse the asteroid belt on the 15th of February 1973. Quite an amazing feat. I think it got out to about 80 astronomical unit and then we lost contact with it. These weren't necessarily the next, but quite important. So, and this is a trajectory it took. It flew in towards Jupiter, formed a gravitational slingshot, picked up enough velocity to escape the solar system, made its way outwards. Whether it got there or not, who knows? No prizes for this one. Yeah, this is Voyager 1. So Voyager 1, not necessarily the next in line, but certainly a very important probe, was launched 5th of September 1977 for the once-in-a-lifetime alignment, although it's more like once in every 3 lifetimes. And the idea was to slingshot it past 4 of the major planets and towards the outer solar system from Saturn. And in 2012, it became the first interstellar probe, or it crossed the 122 astronomical unit boundary. And shortly followed by, not really, it was preceded by, because it was launched 16 days earlier, was Voyager 2 on the 20th of August 1977. And instead of exiting at Saturn towards the outer solar system, it continued on to Uranus and Neptune. It didn't go on to do Pluto because I think they held its trajectory back so it could study Titan for longer, because it was recently discovered it had quite a thick atmosphere, which was more interesting than Pluto apparently. This did continue on to Uranus and Neptune and became an interstellar object in 2018. And the fact that we can still maintain contact with these probes is to me pretty incredible. These are the 2 trajectories of Voyager. So you can see 1 and 2 there and where they diverge at Saturn and Neptune respectively. Other notable examples include Galileo in 1989. This did a flyby the main asteroid belt object Gaspra in 1991 on its way to Jupiter before plummeting into its atmosphere and being crushed. Cassini-Huygens in 1997 did a flyby of Mirsky, and this was on its way out to Saturn. And Rosetta in 2004, or launched in 2004, did a flyby of Steins and Lutetia 2008 and 2010 on its way out to Comet 67P. And that was a really fantastic mission. So NASA Dawn, coming more into the present time now. It was 5 years ago, but it's the most recent thing we've sent there. It was the first probe to reach a minor or dwarf planet. It narrowly beat New Horizons, reaching Pluto by about 2 months. Now, I seem to remember this being on the news for about a week, and then seemingly, although it was a 2-month difference, seemingly New Horizons was everywhere, and people were obsessed with the love heart shape on Pluto, rather than this really cool thing we've seen up close in the asteroid belt. And they were launched a year apart, so New Horizons really zipped by to get to Pluto in time. Its mission was to orbit Vesta and Ceres sequentially using ion propulsion, and again, this was another first. It had conventional chemical and ion propulsion motors, and it remains in uncontrolled orbit now around Ceres. It ran out of its hydrazine chemical fuel, which it needed to maintain altitude control, and its ion thrusters all packed in long before that. Just to give you a quick overview of what Dawn did. Here's a sequence on the right, and you can see 2007 we launched from Florida Cape. 2009 it reached Mars and did the slingshot towards Vesta. 2009, about 7 months later, about 9 months later, can't count, it enters the asteroid belt. A couple of years after that, it enters the orbit of Vesta, and it's the first object to orbit a main asteroid belt body. And then 2012, it departed for Ceres, which it cruised along to for 2.5 years. Took its first image of Ceres in January 2015. In March, it entered Ceres orbit. And again, this was another first. This was the first orbit of a minor or dwarf planet, again, narrowly beating out New Horizons. In July 2015, mission activities finished. In November 2018, we sort of lost contact with it, and it's either plummeted to the surface of Ceres or it's just drifting around in a dead orbit now. So some future missions, and I've put ish there after the first one, OSIRIS-REx, because it's not really going into the asteroid belt, but it is an important thing to talk about. OSIRIS-REx stands for Origin, Spectral Interpretation, Resource Identification, Security, Regolith Explorer. And basically it's going to touch down on a near-Earth orbit asteroid, near-Earth object asteroid Bennu, around 2020. It was going to happen in 2018, but it was beset with stalls, and I think even COVID has actually offset it by another 3 months. But in October, they're hoping to touch down on the object, recover about 1 kilogram of regolith sample and return it to Earth. This is to study, hopefully, the formation of this asteroid and what makes it tick. Potentially, they'll be doing economic studies to see if there's anything worth recovering on there. ARM is the Asteroid Redirect mission. Now, this is probably the most fun one. The mission is either, it's undecided, the mission is either, or will be, to either capture a small size asteroid or to remove a large mass from a big asteroid. The idea is that you can change its gravity in such a way that it will deflect away from its Earth trajectory if that was to happen. The target is unclear. It's likely to be an NEO group object rather than the asteroid belt, just because they're far closer. There are no specified missions to return to the main asteroid belt just yet, which is a shame, but I guess there's no real reason to. Progress on mapping asteroids. NASA continues to monitor them using dedicated orbital satellites and ground-based telescopes as well. So Pan-STAR 1 in Hawaii and NEOWISE, which sits up in low Earth orbit. So in geostationary orbit. NEOWISE is often hibernated and reactivated. I'm not sure why, whether it needs a dedicated team, unclear. Pan-STAR 1, however, is in continuous operation on Mauna Kea, regularly processed by the locals, as I'm sure is quite topical at the moment. And the goal is to keep mapping and tracking these objects, working with CNEOS, which is the Center for Near-Earth Object Studies, and NASA's own section, PDCO, the Planetary Defense Coordination Office, and probably even Trump's Space Force when it gets ticking. So why is this important? Well, there are currently over 14,000 objects that we consider hazardous to Earth. These are near-Earth objects, which basically means they're within 1.3 astronomical units from the Sun. 14,000 is quite a large number. They are quite fairly spaced out, but you know, it's important to keep tabs on them. And themes of future missions are seemingly in defense, as we've just talked about. Any previous or historical proposals to deflect asteroids have involved pinging a mass into them, so deliberately flying a probe into one and hoping to knock it off its trajectory, or the fail-safe, or so we hope, is to detonate an ICBM next to it and knock it off its course. NASA seem quite keen to avoid the latter option for obvious PR reasons. And secondly, going forward, I think commercial interest is going to drive a lot of these studies as well. So there are quite a few proposals for near-Earth asteroids, particularly from China, regolith recovery missions, for research and study of the early solar system, but mainly probably to determine economic viability of asteroid mining. And just out of interest, hopefully I've been about half an hour. The final slide. This is asteroid 16 Psyche. It was discovered in 1852 by Gasperi, the guy who discovered Hygiea, and it was located in the main asteroid belt at a distance of about 2.7 astronomical units, which is again comparable to Ceres. However, this one is thought to be 92% iron, nickel, and gold, and it has a mass of that big number there. And in 2019, it was estimated to be worth $700 quintillion, and that's 700 with 18 zeros after it. And if you were to distribute that wealth across Earth, it'd be enough to give each citizen about $93 billion. So we'd all be as rich as Bill Gates, assuming inflation doesn't kick in. NASA have said that a visit to 16 Psyche with a probe covered in magnetometers and other mineral detecting equipment could be feasible around the 2026 timeframe, but I really don't think there's a driver there for it yet. And even if we did look at this for mining purposes, I think you'd struggle to get all that material back to Earth. So that was a whistle-stop tour of Ceres and hopefully the asteroid belt. I hope you found it interesting. I found it interesting to learn about. If you have any questions, I'll do my best to answer them. So thank you.
Thank you very much, James. What we will do is, can you end your slideshow, please?
Yep. Brilliant.
Okay, and as usual, ladies and gentlemen, if you have a question, can you put your hand up, and I will try and spot you on my screen and turn on your microphone so James can answer you. So, questions. Anybody got a question? Okay, Peter. Good evening, Peter. Peter, you need to turn on your microphone.
Okay, I think I've done that. Can you hear me?
Okay. Off you go then, Peter.
Thanks, Ed, for that very interesting talk. I was interested in that strange mountain on Ceres. Una, was it called?
It was Una Mons, I believe. I'll find it again for you.
It doesn't really matter. You said it might be due to an impact on the opposite side of Ceres, and I just wonder if there is a big crater on the opposite side.
The thing is that there are many on that side of Ceres, which makes it quite difficult. But that theory is based off observations on Mercury and more or less seeing it happen in quite recent craters, perhaps within the order of 1 million years ago. It's quite strong evidence for it on Mercury.
I would have thought it might have to be a particularly big one, that's all.
Yes, certainly would. Enough to send a plastic ripple wave through the crust. Yeah, quite substantial.
Okay, Peter?
Yes, thank you.
Trevor?
Hi. I just wondered if Ceres has done any shepherding of the smaller asteroids, like around the rings of Saturn. You've got the shepherding satellites that seem to carve tracks. I wonder if any tracks have been found.
I'm not sure on that, but it would be interesting to look up, and I'm sure it probably has. For an asteroid, it's certainly a large object. For a planet, it's certainly a very small object, but yeah, undoubtedly it's had some effect. Can't answer that, sorry.
Okay, Trevor.
Thank you.
Anybody else have a question? Philip? Philip, turn on your microphone.
It's gone off. It's gone back on again. Can you hear me now?
I can hear you now.
Yeah, I don't know if it's a question or an observation, but it's a bit complicated. But when you look at, like you were saying earlier about there should be a planet where the asteroid belt is.
Yeah.
After 4.5 billion years in the solar system's existence, if there were going to be a planet there, it'd be already there. Perhaps Jupiter's such a big influence in that part of the solar system. And when you look at where the asteroids are, the Trojans and things around Jupiter and the asteroid belt, how they're in front and how they all rotate around each other, perhaps Jupiter stops actually planets forming any bigger than Ceres. Otherwise, they'd be there already after this length of time. And perhaps it's just like a giant washing machine where it's rumbling these planetoids around each other, and they're bumping in and breaking up, adding together, building and breaking apart. And I suppose the other thing is, if there are like a volcano on Ceres, perhaps it is large enough to have a molten centre, or it's hot enough to produce volcanic eruptions, perhaps, or has in the past. I don't know. I just wondered if you concurred with that kind of thought.
Definitely, the point about Jupiter, certainly, that basically has stopped in the past and still stops today. I think Ceres getting any bigger than it actually is. And I'm not sure on the mechanism. I remember seeing it a few years ago in a Brian Cox documentary, but yeah, Jupiter did move quite rapidly through the early solar system, and it threw out a lot of debris that could have gone on to form planets, and certainly swept away a lot of material that would have stayed in that region of space anyway. It certainly has stopped the formation of planets there. Maybe it would have gone to Mars if not. Can't comment further.
Just as a comment on that.
Yeah.
There are two large groups of asteroids called the Trojans and the Greeks.
Yeah.
60 degrees ahead and 60 degrees behind Jupiter, and there's a lot of evidence that there is movement. They migrate
between them
and the asteroid belt themselves. So it's a very dynamic area.
Yep.
Okay, Philip.
Thank you, Philip.
Roy, let's have a quick chat.
Sure. Yeah.
Okay, Roy. Turn on your microphone, Roy.
Talking about future missions, I believe there is a proposed mission to go to the Trojans, which in essence is asteroid belt material, hopefully. So I think it's going to visit what's the Trojans, and I think it's also going to go to the other side, which are are they Spartans on the other side? Greeks.
The Greeks.
The Greeks. So there are plans. I think it's before 2030 that they're planning to launch this thing.
Yeah, the slide I had was just in terms of the asteroid belt itself, but then I digressed onto major projects. But yeah, so I think China have got 3 in the works for about 2024 timeframe, landing on all sorts.
Yeah. Trouble is with China is they don't share their stuff as readily.
No.
Okay. Anybody else got any other questions or anything to Peter?
Can I just add a comment? I was very intrigued by your diagram of the asteroid belt, showing the asteroids in a sort of triangular formation that was rotating with Jupiter. Is that real? How can it stay like that?
I believe so. There's some effect, some gravitation effect called the Kirkwood gap effect. I'm really not sure. Is my answer. But yes, that is a real simulation. That was based on data up to 2005.
Peter, that animation was showing the concentration of the Greeks and the Trojans.
Yeah.
Yes, but in red it showed a triangular formation.
Yes, and that's the movement of the asteroids from the Greeks, the Trojans, and the main body of the asteroid belt.
Oh, I see. I'll have to think about that one. Thank you.
Yeah.
I think every revolution, 2 of the spokes of the triangle go into contact with the outer asteroids. It allows them to intermix.
Okay. Anybody else got any other questions? Gary, unmute your. Okay, Gary.
Well, the Trojans, the Greeks, are the Lagrangian points, so they're the gravitational stable points within the orbit. That's why they sit pretty much where they are. Yes, they do vary a little bit. They effectively orbit around Lagrangian point, but that's why they're there, and that's why we put spacecraft into Lagrangian points around the Earth.
Right.
Thank you.
Thank you very much.
Another quick couple then. You showed a picture right at the beginning of a crater that you said was the Chicxulub crater.
Yep.
That's not the Chicxulub crater because that's in the ocean. That's Barringer crater in Arizona.
I thought that was Chicxulub. I thought that the actual impactor fragmented. I've seen the giant ring from 60 million years ago that does go into the ocean, but I thought that was a remnant of Chicxulub.
No, that's Meteor Crater. It's about 50,000 years old. The reckon Meteor Crater in Arizona.
Okay. Apologies then. Yeah.
No, it's all right. I only know because I've been there.
And it's not an ocean.
Anybody else got any questions? Okay, so can we display our appreciation in the usual way, please? Just by having a quick wave, and thank you very much.
Thank you. Hope it was interesting.